Hello everyone, my name is Geeta. Over the past decade, I've built and deployed ML and LLM systems at scale across FANG companies, focusing on turning research models into production grade systems. If there's one mistake I've seen repeatedly, it's expecting models to magically know things they were never given. And that brings us to today's topic, RAG, because LLMs have amnesia. Let me start with a slightly provocative statement. Large language models don't actually remember things. They sound smart, they do write beautifully, and they reason impressively. But at the end of the day, they have amnesia. Everything they know is frozen at training time. They don't know your data, your documents, or what happened yesterday. This is the talk about how we fix that problem. Retrieval-Augmented Generation, or RAG, is how we give LLMs something that they've never had: memory and context at runtime. LLMs are powerful and they're one of the most transformative technologies we've ever built, but they come with real limitations and that matter a lot in production. First, they are trained once and then frozen in time. There's no real-time awareness, no live updates, no built-in freshness. Second, they do not have access to your proprietary data, proprietary documents, internal policies, or domain knowledge. And most importantly, they do not have fact-checking capability. So that's why we see hallucinations, and LLM does it very confidently, and it very confidently makes something up. So the key takeaway from previous slide is that they generate language extremely well, but they don't actually know things until we give them context. So this is where retrieval augmented generation comes in. RAG fundamentally changes how LLMs operate by giving them dynamic access to external knowledge at inference time. Instead of purely relying on what's baked into the model's parameters, we retrieve information from relevant documents, databases, or knowledge graphs. That retrieved information is then injected directly into the prompt, and this is called augmentation. In simple terms, RAG gives the model the memory it never had during training, and this intelligence is used for generation. My favorite way of explaining RAG is with this in exam analogy. Without RAG, LLM is like a student taking a closed booked exam. It has to rely entirely on memorization. If it doesn't remember something exactly, it guesses. With RAG, it's like an open book exam. The student still needs intelligence, but now they can refer to the book or any trusted material. In this case, LLM is the student and the knowledge base is the textbook, and the retrieval system is the indexing, like in a book, and the prompt is the exam question. The same model, but it gives different outcomes. RAG isn't just a technical improvement, it completely changes the economics of the AI system. Instead of training massive, expensive models to memorize everything or to get fresh data, RAG lets us use smaller, cheaper model and gives them access to knowledge when needed and up-to-date knowledge. That reduces the need for constant fine-tuning, which is slow, costly, and brittle. Another huge advantage, as I've mentioned, is the freshness. You don't need to retrain the model, you just need to update the knowledge base. Of course, there is latency trade-off. Retrieval adds latency, although it is in extra milliseconds. It requires some tuning of the chunk size, embedding models, the in and index. But the well-designed RAG system stays fast enough for production while being far more accurate. This is exactly why products like Perplexity work so well. They are not only smarter because of bigger models, but because of better retrieval systems. This slide shows the full RAG pipeline end to end. Documents are first encoded into embeddings and stored in a vector database. When a user submits a query, the same embedding model is used to create an embedding, and we then perform similarity search to retrieve the most relevant chunks. Those chunks are combined with the prompt and the user query and passed to the LLM as context. The model then generates response which is grounded in the documents that is retrieved. The key idea here is that RAG is not a single component, it's a system with multiple moving parts. Now let's move on to the chunking strategies. Chunking is one of the most underestimated design decisions in RAG. There are several strategies that are showcased here. Fixed size chunking is the most simplest. Basically, we split text into equal length chunks with some overlap. This is simple and fast, but sometimes it may break the semantic meaning. Semantic chunking is the next kind of chunking where sentences are grouped by semantic similarity. This preserves meaning better but has a higher computation cost. Recursive chunking is a great default. We can start large and only split when necessary. The next one is structure-based chunking. Let's say we have documents which are very well formatted, like manuals or research papers which has title intro sections. Now we can use this structure to form our chunks. The last chunking technique is LLM based. Now we can also use a LLM to decide chunk boundaries, and this is of the highest quality as you can guess, but this is slower and very expensive. The bottom line is that bad chunking leads to bad retrieval and bad retrieval leads to bad answers. That is why this step is very important. The next step that I want to focus on is the embeddings and retrieval. Once the documents are chunked, each chunk is converted into a dense embedding, and these vectors capture semantic meaning and not just keywords. All embeddings are stored in what we call the vector database along with original text and metadata. When a user asks a question, we embed that query in the same vector space as you can see, and then we perform what we call the ANN, the approximate nearest neighbor search, to find the closest vectors. These vectors, using these vectors, which correspond to the most similar chunks, we get these chunks and are passed downstream for context injection into the LLMs. At this point, retrieval is done. Now the generation begins. The retrieved chunks are injected into the prompt template alongside the user query. This is critical. The model is instructed to answer based only on the provided context. The LLM then generates a grounded response and the output is streamed back to the user. The model isn't just smarter, it is simply better informed. This is the most important slide in the deck, although it is not as dense. The RAG performance doesn't come from clever prompting alone. it comes from a system design. You can tune chunking strategies, embedding models, indexing, ANN parameters, retrieval depth, prompt formatting, and so on. Small changes in retrieval often have a bigger impact than changing the LLM itself. The core principle is simple. Better retrieval leads to better context, which leads to better generation. And with that, let's move on to the demo and see the system in action. In this demo, I'm going to show a minimal end-to-end retrieval augmented generation pipeline built completely locally. The key idea is simple. Instead of forcing an LLM to memorize everything, we retrieve relevant documents and then inject them into the prompt. I've run this before just to make sure that it is ready for this demo, but let's run it in real time. Okay. Okay. So the first step is just standard setup, imports for processing, embeddings, and so on. Here in the second cell, I'm just downloading a sample PDF. This could be your own PDF in like your own path and so on. At this stage, we are not doing anything intelligent yet. We're just converting loading a raw document, and then we are trying to extract the text from this PDF. Here we can see this particular PDF I have has 179 pages, and there is an example snippet here. As I've gone through in the presentation, chunking is the most important step. Here I have a very simplified version of chunking. What I am doing here is the pages that we loaded before, I am just defining a chunk size of 10 sentences. This is intentional, just to keep a few sentences together as a chunk. And next, I define a small helper function to group these sentences into a chunk. This is like creating like a paragraph like unit. Now what I'm doing is I have an empty list, and then in this and then we loop over each page, and then I'm using a Spacey library where I'm splitting using this library to split them into sentences. And here I have a list of sentences. Once we have the list of sentences, I'm using the method so that we can group them into chunks of 10 sentences using the helper function, the split list. Now once we have the list of sentences, we can do stripping some white spaces, removing white spaces and so on, but we can also add the page number and everything so that we can keep track of things. Let me just run this. Okay, so yeah, as you can see, this is not at this point we've transformed raw documents into semantically meaningful chunks, and these chunks are now ready to be embedded, indexed in files, and retrieved at query time. I want to leave with this thought. Good chunking is the foundation of good RAG. If retrieval fails, it's often not the model, it's the chunking. Now we convert each chunk into an embedding vector. Here I am using sentence transformer library and a model called All Mini LM which has layer 6 and version 2. This is how we can load the model from the sentence transformer library. And since we already have it in a data frame, the df chunks, I'm converting them to a list and then encoding using the embedder model. So this is simply a step where dense numerical representations are created to capture the semantic meaning. Basically the similar texts end up closer in the vector space, and most importantly this step happens offline. We can see this cell running. It's just taking a minute, and you can see it is processing it in batches because I've given a batch size, and now it's done. The next step is creating the FIAS index. FIAS is just a vector index that allows us to efficiently search through thousands or millions of documents. We are using what we call the inner product index with normalized vectors, which gives us a cosine similarity. This is our system memory. So let's just run this. Here currently the index size is just 1843 chunks. Now let's move on to the retrieval function. This is our retrieval in our retrieval-augmented generation. So far we've built an index, and this is the first time we are going to query our knowledge base. The retrieve top k function gets the user query and then returns the top k nearest documents or chunks from our document. First we will convert the query into a query embedding, and we'll here what is important to note is that we are using the same model to encode the query, same one that we used to encode the documents. Next we are also like normalizing just how we normalized for indexing, and then what we are doing is we are just now searching the index with this query embedding and asking for the top k neighbors. The scores are our similarity scores, and the indices are the indices of the matching chunks. Here in this loop we are looping over the retrieved indices and reconstructing the results. For each match what we are pulling is the similarity score, the page number, and the actual chunk of the text. In the print results method, this is just like for a visualization helper for us. It just lets us inspect the retrieval quality before involving an LLM, which is a very critical debugging step in any RAG system. So let's just do a quick test. Let's say I want to test what is the documents we are retrieving for a question. What are question meaning the query, what are the macronutrients and what do they do? Let's run this and see. See, this is so quick. For our query, it has retrieved 3 because I said my k is 3 here, and it is getting the chunks which are relevant, which is talking about macronutrients that are needed in large amounts. And there are 3 classes of macronutrients called the carbohydrates, lipids, proteins. And the second one that it retrieved with a slightly lower score, it is talking about the basic concepts in nutrition and how it the factors that affect the nutritional needs. So slightly less relevant, as you can see from the description here. And the last one it retrieved is again looks like it is getting the context from a figure which is saying the micronutrients are carbohydrates, lipids, proteins, and water proteins, etc. So we can see that the retrieval looks fairly accurate. Now we can proceed to how we can use it in the LLM to answer a question. So here what we are doing is prompt construction, this is where the augmented generation is happening. Up until now we've looked at retrieval and how related chunks are retrieved. This is where we are combining the retrieval with language models. Okay, here I am using a small local language model. I'm using the Hugging Face Transformers library, and I'm trying to use the Microsoft Phi, which is like a small model because I am trying to call it on my local. This is intentional, and luckily for us, RAG allows us to use smaller models because the knowledge comes from the retrieval and not from the model memory itself. In the format prompt method, this is the heart of the RAG. It takes the retrieved context, basically the contexts that are retrieved, and injects them into the prompt. Here, each retrieved chunk, along with its page number and similarity score, is ingested into this prompt here. And the system is explicitly telling to use only the provided context, if you can see here. And if the context is insufficient, we are instructing to say I don't know instead of hallucination. This is one of the hallucination reduction technique. Now we are loading the tokenizer for this particular model ID. This tokenization is how the raw text becomes model readable numerical input. We then what we are doing is just making sure that it is using the CUDA that I have on my local, and making sure that we are loading in 4 bits if it is available. This allows us to run the model efficiently on consumer GPUs, even with very limited VRAM. If quantization is not available, it is efficiently gracefully falling back to FP16 on GPU and FP32 on CPU. Here the RAG performance itself, RAG architecture itself doesn't change, only the performance is what is going to change. Now we load the model with these settings, and this step initializes the generator, but it still doesn't have access to our documents. The answer function ties everything together. First, using the retrieve top k, that the method that we've seen before, it is retrieving the most relevant top k chunks, and these chunks are just formatted into our prompt, and this is our augmentation step. Now we are using our tokenizer to tokenize the prompt into something that the model can understand. And finally, this is where this tokenized input is sent to the LLM to generate an answer for us. And this is where the LLM also gives us tokens back, and we are decoding into readable text here. So what is critical here is the language model has no idea that files exist. it doesn't know what embeddings are. All grounding is happening through the prompt. Now let's ask this question and see how it answers. I just ran it. Let's see. It's loading the model. It just takes a minute for it to answer. As you can see, it first, because we are printing some things, it's giving the context, like it is showing us all the context that it is using, and this is the answer that it generated. For this question, what are macronutrients and what roles do they play? Macronutrients are nutrients required by the body in lesser amounts but are still essential for carrying out bodily functions. 3 classes of macronutrients: carbohydrates, lipids, and proteins. As you can see, this is generated by the LLM, but using the context that it received through the retrieval. This is a retrieval-augmented generation in its simplest and most transparent form. Getting the relevant knowledge, injecting into the prompt, and let the model reason over the trusted context. This exact pattern scales from a notebook demo into production systems used at enterprise scale. With that, I end the demo, and I really hope that you've enjoyed learning about retrieval-augmented generation and how it helps with LLM hallucination and grounding in the domain knowledge and so on. Thank you for listening to me.